Is somebody missing from outside? Okay. All right, well, it's a real pleasure. Thanks for coming. It's a real pleasure to have Alvaro De Rujula here. But before that, I would like to thank, well, nowadays we only have one representative of the La Pietra families, Barbara Amonson, but this series of lectures and many other things are financed generously by the De La Pietra families, Stephen, Pam, Barbara, and Vincent. And we are always grateful to the fact that they allow us to bring or invite some world speakers and for everybody to profit. Tomorrow there will be a lecture to high school students, and hopefully we'll have about 200. And then there will be a more technical talk that Alvaro will give on Thursday, also in this particular room. Well, I don't like to make long introductions, but I think just a minor profile of Alvaro. He got his BA and his PhD in Madrid, where he was also then soon become a professor, teaching various courses at the university. He was in the Spanish Center for Nuclear Studies. Then he was a postdoc at CERN and visiting Trieste, several centers in France. And eventually he ended up at Harvard in the early 70s, and he benefited or contributed to the golden 70s in the making of the Standard Model, together with Shelley Glashow, with David Politzer, Howard Georgi, and various others. And after Harvard, he ended up at CERN for a certain number of years, where he even was the head of the theory group for a number of years. He was elected to the European Academy of Sciences, and now he's a member of the Institute for Theoretical Physics in Madrid, as well as an emeritus professor at the CERN laboratory. So please, Alvaro. Thank you.
Thank you very much for the introduction, and thank you to the La Pietra family for having this kind of occasion. And one thing that Luis forgot to say is that I used to be his boss, and that's how he learned to run an institute, which he's doing now. Now, since I am a theoretical physicist, I do not trust electronics, so I'm going to start with some tests. These things seems to be working. I plan to talk about the value of pure science, or another title would have been the Higgs boson and the coronavirus. And what I really want to talk about is the role of basic research, that is to say the one which is knowledge-driven and not spin-off directly money-driven, after the times of the pandemic. Now, I said Higgs boson. What is a Higgs boson? A Higgs boson is an elementary particle, that is to say one object that if it has smaller pieces we don't know about, so for the moment we consider it elementary. There is nothing inside it. And with an average lifetime of some 10 to the minus 22 seconds. So that's rather brief. And it's an American billionth of a trillionth of a second. And the question is, what could be more useless than the search for this kind of thing? Now, in my talk, I'm going, since I'm Spanish, to organize things our way. That is to say, instead of giving you a lot of something, I'm going to give you tapas of several things. For instance, I'm going to talk about Higgs at CERN, and COVID-19 and genetics, and the climate issues and CERN, and in general, why basic research. Now, I have said CERN. CERN is the European Center for Particle Physics. It's in Geneva in Switzerland. And this is information about it a few years ago, 2018. And by then, it had 2,300 people who are paid by the laboratory, and the rest of the people are so-called users. That is to say, people from universities or labs that come to use the facilities of CERN. It had, now it's 25 member states, I think, and 7,800 and something people from those states. Russia is not and was not a member state, and it had that many people, over 1,000, almost as many as Americans at the time. Now, the situation with Russia is complicated. I'm not going to talk about it. There are also a lot of Chinese, something like 510. And there are people from about 109 countries, which means about 350 different languages, which you can hear in the cafeteria. You you walk 10 meters and you cross 5 languages. Now this is what it looks like, the location of CERN. You see a little line of dots that divides Switzerland, which is to the south or to the lower part of the transparency. You see the airport of Geneva, and to the north, above the little dot line, there is France. And underground, there is some object that has 24 kilometers in circumference that I will talk about in a moment. It is called the Large Hadron Collider, and it is at a depth of about 100 meters on average. Now you notice this line in here, and if you look at a particular point, for instance there, you have the impression in this aerial picture that everything is the same to the south, that is to say Switzerland, or to the north, that is to say France. But if you take a picture with higher resolution, things are very different. All gardens are like this in the houses in Switzerland, while in France they are all like that. And that's only a distance of 100 meters or so. Now, what is done in such a laboratory? Well, people take hydrogen atoms, like the one here, a proton and electron. They ionize them, they split the two objects, and the proton is injected into what's called an accelerator. And it consists of various pieces accelerating the particles to higher and higher energies, and it eventually goes to the big machine, which is a collider, that is to say something that is going to have beams moving in two opposite directions, such as in a highway. And now this is someone imagined this way of the protons being accelerated electrically and guided magnetically in what's called an accelerator. A proton is made of 3 quarks, it's not an elementary particle, and protons come from one side or the other of detectors, and they are made to collide when they reach the detector, as in here. And pumba, when there is a collision, a bunch of other objects is made on the spot. It's created at that moment. It wasn't there before. Now, another time the same picture. This is a highway, but it's peculiar because it has 4 crossings in which you can hit the traffic coming on the other side. And when that happens, you make new things by converting energy into the mass and energy of new objects. And that seems to be a very simple diagram, but the images that are taken of these collisions are taken by things such as this, tremendously complicated, essentially photographic cameras, but a little bit more complex. And to give you an opinion, vision of how large these things are, you have a couple of people up there. So these are enormous detectors that see what happens when you collide 2 protons. And in this case, which is a reconstruction of an event is a collision that has been recorded, something happens there that makes 2 particles of light, which are called photons, in more or less opposite directions. And this may be something due to a Higgs boson that decays, it disintegrates itself into 2 photons. And this is not a picture of the first observed Higgs boson, it is a picture of the first collision ever made, seen by one of these collaborations. There are 4 big collaborations around the ring. And who you see here is not Madame Merkel in her youth, but it could have been. And what you see here is that also that work for scientists is like for everybody else. That is to say, there are the 2 guys who worked all night to make this possible, and the others who are having fun. And, well, there are about 20,000 people working in a lab such as this. What do? They do research and onto the fundamental constituents and forces of nature, and the reason they do that is in search of knowledge and nothing else but knowledge. That is to say, the most precious object. So, a few years ago, they discovered the existence of this particle called Higgs boson, And why should anyone care? I repeat. Oh, something happened, which is not good. Ah, shoot. It's going to work. Maybe. Yeah. Suppose that I empty completely this room. It wasn't that it stopped, it's that this transparency is supposed to be black. So you take this room, you take the lights off, you take the air off up to the last molecule, you empty it completely, you cover it around with a shielding such that nothing is left in, and you think you have made a vacuum. There is nothing else left, provided we also had left. And that's not true, and you are aware that that is not true because there is something called the gravitational field of the Earth, which is exerting a force on you that is helping you sit down. But suppose I now take the room to a place in the empty space of the cosmos where the gravitational forces in various directions are up to zero, then you think that is nothing left. But that's not true. Even if we go there, there is something left in the vacuum of this universe, which you cannot take off, you cannot subtract it, and it's called the Higgs field. And that is the field whose vibrations are the elementary particles called Higgs bosons. And why do you care about this? Well, for instance, if there was no Higgs field, the electrons would be massless, then they wouldn't bind to protons to make atoms, and if there are no atoms, there is no coronavirus, but there is also not you. And so that solves all problems just by getting rid of the Higgs field. Again, I pushed the wrong button. Yes. Sorry. Try to be more careful. Now, when you do fundamental research, one thing that you ought to ask is whether there are spin-offs to it. The most important spin-off of CERN, of the fundamental research made at CERN, is due to this gentleman called Sir Tim Berners-Lee, who invented a language called Hypertransfer Text Protocol or something, Hypertext Transfer Protocol, which is the way in which he managed to have people in the laboratory doing different experiments and having different computers, have their computers be able to talk to each other. That is to say, he invented a language, a universal language for computers to be able to connect to each other. And that's what made the enormous progress on internet since then. And it's something that he says he had in his mind since he was a child. He wanted to have a way for everybody to talk to everybody. Unfortunately, he managed. Now, since this is a place where fundamental research is done, there was not a patent associated to HTTP. Imagine that the CERN was to ask for 1,000th of a dollar per megabyte transmission. CERN would be by far the richest object in the galaxy, and we certainly would have no problems. But there are other things that this one you may have known, but there are other progresses started at CERN which you use every day, which is the touch screens, for instance. One of the first touch screens was made at CERN. Now, enough for CERN. Let me talk now some about biology and genetics. You all remember that Mendel did experiments with pea plants and discovered the rules of heredity in the middle of the 19th century. A little later, Darwin published his book, The Origin of Species, where he postulated correctly that there is an evolution from one species to the next. And going ahead with biology, a crucial discovery was that of Watson and Crick in 1953 of the double helix of DNA. And in my opinion, they won the Nobel Prize for one sentence in their paper, which was the last, which was, "It has not escaped our attention that the specific pairing we have postulated immediately suggests a possible copying mechanism for the genetic material." That is, they understood in practice how one inherits features from one's parents. Not very often emphasized is that the work was based heavily on crystallographic analysis by a lady, Rosalind Franklin, and a gentleman, Maurice Wilkins. This used to happen often. In any case, the basic research has made an enormous progress since 1850 to the study of the virus genome of this particular virus genetic structure. Now here you see a picture of the COVID, coronavirus virus, and it is taken with an electron microscope. It is taken with an electron microscope because of something that we understand thanks to quantum mechanics. That is to say, if you want to discern the structure of something, you have to look at it with a wavelength of light or electrons smaller than that something, so that you see the details. And for a given fixed energy, the wavelength of a beam of electrons is smaller than the wavelength of a beam of photons. And that is to say, with an energy which is not enough to destroy the object, you can still see its structure. So something tremendously incomprehensible, such as quantum mechanics, allows us to do things like this. Now, this is a presumably correct estimate by me of the status of the audience when I am about 1/2 through my talk. Now, another interesting thing having to do with these basic rules of nature that are so difficult to understand for those who do not study them, and even more for those who do, is the following. There are objects such as penguins or electrons called fermions, such that if you collect them inside a box, there is a moment in which you cannot add another one because the box gets filled. And there are other things also based on peculiarities of quantum mechanics that are not called fermions, are called bosons, for a reason that was discovered by Bose and Einstein, that we call statistics, although it has very little to do with statistics. And that is, there are objects such that you can always add another one in the same state to any place where you accumulated them, such as the metro in New York. It is also true that you can always add one more person there. And those are called bosons, and the particles of light called photons are an example of a boson. And it's even more peculiar, because if you keep on adding bosons in the same state of momentum and direction and so on, polarization, it becomes easier and easier. Instead of getting the place full, you get the place such that it wants another one of the same. And that's the basis of the laser, which is, for instance, now essential in ocular therapy. Now, this is a list of research, things that have happened in basic research that have had an enormous impact on clinical medicine. For instance, X-rays, born, so to speak, in 1894, are the basis for computer-aided tomography. Antimatter, something so extremely peculiar, is the basis of positron electron tomography, or whatever it's called. Nuclear magnetism is the basis of magnetic resonance imaging. Radioactive isotopes are used in brachytherapy, that is to say, curing cancers with radiation, for instance. The accelerators, the first of one ever built was called a cyclotron, allow you to have particle beam therapy. Lasers, I have already mentioned, are useful in microsurgery. something called polymerase chain reaction, which you now have heard a lot about because it's called PCR, is used in forensic medicine originally to find who was the murderer, and now to find whether you are infected or not. Penicillin, which was discovered by chance, certainly controls diseases. The structure of DNA is used in gene therapy, and so is CRISP, this one very recently. And the peculiarity of all these things is that they were all made exclusively as research in basic science with no intention of being useful. And by the way, each of them got a Nobel Prize. And that I stole from a talk of our colleague Sheldon Glashow, this list. He likes lists of Nobel Prize winners since he is one of them. Now, of course, I made a mistake again. By the way, there's a statement by a British Nobel laureate who I like a lot and has to do a lot with what I'm trying to say. The statement is that applied and not yet applied should be the two ways in which you refer to research. And one interesting question is how much does it take for a basic discovery to become a useful something or other? And if you look at Newton and his probably untrue apple and so on, it took till the first application, which was the Sputnik, 271 years to go from theoretical physics to practical applications. Now, if you take the Maxwell's equations of electricity, magnetism, and light, which is an electromagnetic wave, which I wrote here in one of the modern ways of putting them in shorthand, till Maxwell published his equations, till the discovery of William Hertz, that one could emit and receive electromagnetic waves, that is to say, the invention of the radio, TV, etc., that took only 27 years. Now, under pressure, some politicians rely on scientists to make progress in some direction. And then the elapsed times may be much shorter. One story, which is probably fake, is that Archimedes had the idea of using mirrors to break the Roman siege of Syracuse. That is fake news, apparently. But what is not fake news is this one, and it's an example of a similar nature about which I don't need to talk. But since I just didn't mention him, this is a picture of Mr. Einstein writing his equations of general relativity, which are these scribblings in here. And even adding to them a little extra term that explains, in a moment I'll tell you what. Now, these small equations are not so easy to interpret, but they describe with fantastic accuracy the orbits of planets, the existence and properties of black holes, the gravitational waves, and the entire expanding universe. It is amazing that a few lines of scribbling can tell you all this. And nobody has found an example where the equations turn out not to describe reality. And they also, allegedly, this extra term that I put there, which by the way is the energy density of the vacuum, should explain the accelerated universe. These equations are so known that if you travel in a desert in Bolivia, you can find them like here. Now, one of the things that these equations imply is that time is relative. And if you have GPS satellites, there are two effects that are relevant to them. One is the special relativity invented by Einstein in 1905, and the other one is the general relativity, which he invented in 1915. Now, without relativity, the GPS would not work because the clock in the satellite works more slowly because it's flying relative to you, and it flows more rapidly because it's further away from the gravitational pull of the Earth. So there are two effects, they do not compensate, that you have to take into account if you want your GPS to take you where you are going and not there. And so special and general relativity are something that you use every day. By the way, the GPS around here drives me crazy. There are no straight lines or 90 degrees crossings. Another interesting question is whether someone not doing basic science would have made the mentioned inventions. For instance, the protocol that allows the web to work, even more so without patenting it. The answer is no, in every other case that I know. For instance, if you are an artilleryman, since I did the military service under Franco in the artillery, you may ask, would I have invented Newton's law such as to aim better my cannonballs? And the answer is most probably not. And someone working at Bell Telephones, would he or she have invented Maxwell's laws of electromagnetic waves and light to improve radio communications? In every case, the answer is perhaps, but it was never the case. So there is something to say for fundamental research. Now, this is one of the 2 or 3 main problems that we have at the moment, as you know. And you may ask whether a laboratory such as CERN is doing something about climate and global warming. And the answer is yes, too little, but something. And there's, for instance, at CERN, an experiment called CLOUD, which studies the uncertainty in the predictions of aerosol particles in the atmosphere and their effects of clouds. The aerosol particles make the clouds more reflective, and therefore they cool the surface, which is the opposite of a concentration of CO2. So what these people have done is to build a model atmosphere, such as you see in here. This is a very small experiment by CERN standards. In the lower thing, they have added by hand some little dots supposed to be the aerosols, and they subject this thing to a beam of protons, like the protons of the cosmic rays that affect the clouds and therefore the climate are coming from the sun and from the galaxy, and ionizing the atmosphere and affecting the clouds. And how this happens is not observationally well known till these experiments were done, and we ought to do more though. And by doing these experiments, they found some surprises. I'm not going to be able to read this, but it says a synergy between nitric acid, sulfuric acid, and ammonia leads to the formation of aerosols at significantly faster rates than those from any 2 of the 3. That is to say, they have discovered that it takes a triplet of bad things to affect the climate by its effect on the atmosphere. Now this is the audience when I am 4/5 through my talk, so only a few minutes are left. There are evil people, like the one shown on the left, if I can stop this. Evil people who often ask me and ask everybody the following question: what did basic research laboratories such as Fermilab, SLAG, Brookhaven, and CERN do about the COVID-19 virus? And the answer is they did all they could. For instance, at CERN, they constructed in a record time a high-energy ventilator to make people breathe when they have difficulty doing it. Should have been called a low-energy ventilator because it's very compact and it runs on a microcomputer with a microcontroller, so it takes extremely little electricity. You can power it with a bicycle and a dynamo, so it's useful in countries that do not have an advanced technology. CERN immediately made 1,000 a day face shields and 10,000 liters of sanitizer gel with a recipe recommended by the World Health Organization, and they protected all the local police stations by plastic screens. And more important than any of this, perhaps, is CERN allowed their enormous computing resources and capacity for those simulations in order to study the evolution and spread of the virus. Now, let me come to the conclusions, which I think are not only mine, because they are self-evident. Basic science is the second best investment possible. The first investment possible, most important, is a good education at all levels. I'll talk more about that tomorrow. In arts and sciences, and respectful of nature, like and not unilaterally nationalistic or otherwise sectarian. Without such an education, there is no progress. Now, this is my penultimate transparency. There was this guy who, in the mountains close to CERN, called the Jura, got lost in the fog, which is always there, on his balloon. And by chance, he went close to the top of a hill where there was another gentleman. So the one up there says, I got lost. Would you tell me where I am? To which the other answers, roughly 2.13 meters above my head. Oh, la, 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 la. You're not going to know the answer in a while. So the one up says, you must be a scientist. And the other one says, why? Because your answer was slow, very precise, and totally useless. And what I try to convince you is that this was also fake news. And at this point, I think I should stop.
Thank you.
Thank you.
Thank you very much, Alvaro, for a presentation. Are there any questions or comments?
This gentleman here.
This might be a little far afield, but I was just curious, what do you think about the prospects for string theory?
You gave me the answer, it's far field. I cannot answer in front of this audience.
Maybe after with the drink. Any more questions or comments?
It's the most beautiful theory around, but it is the most theoretical theory around.
It's the most what theory?
The most theoretical theory, it's also the most beautiful.
Yeah.
So this was a wonderful exposition of what happens in science and why it matters. What question I have is, I've recently visited CERN, where I visited their division which talks about this to the society. And I've been very impressed by the funding that that group has. What advice would you give to other places, not just laboratories like this, but since you mentioned number one item is education of common people and training them to do science and other non-fake activities, what advice would you give to other such organizations? What fraction of money would you be willing to spend on such things?
Well,
what is the impact or importance of that, in your opinion?
Thank you.
I think education is more and more important as you go towards the elementary level. And there are countries such as Denmark, which have an excellent education. The children are very happy and they learn a lot. And one essential ingredient for that is that a teacher in a school is very highly regarded socially and very well paid. Now compare that to the United States and you have the first problem. And I was going to say something else, but I forgot. Yes. There is also the question of one example of how important education is the following. In Switzerland, there has not been a mass murder in the past 21 years. And there has never been a mass murder in a school. So there must be something that is different. And what is different is the education from childhood onwards. Because everybody, practically everybody in Switzerland has a gun at home.
Yep.
So what we should do is, first of all, educate better teachers who are better paid and more appreciated and more numerous. That's my opinion.
Yes, I wanted to ask about touch screens. And the reason I asked, I saw them actually the first time I visited CERN in 1975. And they already worked. I was very impressed. I was a young student then. And how actually did they invent them, do you know? How did they invent the touch screens?
How they invented touch screens? I think they did it for fun. No, I'm sure, I'm serious. I have the papers and they don't give any reason to do what they are doing. The original papers on the subject.
I remember still that they were invented to control the circuits of the accelerator.
Yes, yes.
You touched them and you saw another part of the circuit.
Comfort, laziness, many reasons to invent the touch screen. Controlling children.
Any other question or comment? No, I don't see any. Well, Nikita, you have some comment?
I have a silly question. Do you think there is a connection between this apocryphal story of Newton's apple and the Eve's story and the apple of Eden and the primary sin?
No, you can
Adam and Eve.
answer the question yourself. That's a metaphysical question. It's not my business.
I think Voltaire was involved in creating this story, but I'm curious.
Yeah, Voltaire made it up as well.
Well, Voltaire had a problem with the church.
And with the IRS. He cheated with the lottery.
Since you are at this big international institution, now that we are seeing so much polarization in the world, do you have a sense that this is even creeping into the high level of highly educated people, scientists?
It's dividing highly educated people with highly uneducated people in this country in particular. Now, is it dividing highly educated people? I can't think of highly educated people who would vote for Trump. So yes, you're probably right. There is also a spread of division all across society. The polarization of politics in the world is almost as frightening as the war and the climate problem and so on.
But this probably means that education is not enough. Because obviously,
Education would do a lot, as the examples that I gave show. Comparison of United States with Denmark or Finland or Switzerland. And that, I think, is mainly the education. Of course, there are other things that are problematic, like we are too many. That's not an easy problem to solve.
Any other questions, comment? Well, if not, let's thank Alvaro again. Thank you.